Deposition processes in semiconductor industry. Deposition processes form a fundamental pillar of semiconductor manufacturing. These techniques involve the precise placement of thin films onto a substrate, enabling the creation of the intricate structures found in modern microchips. In manufacturing, deposition is considered a core fabrication process, crucial for constructing transistors, interconnects, and insulating layers. Without reliable deposition methods, advanced integrated circuits would be impossible to build. The resulting thin films are often just a few nanometers thick, but they must be uniform, defect-free, and adhere perfectly to the underlying surfaces. Precision at the atomic level is essential to meet the performance demands of today's semiconductor devices. From a technology perspective, two dominant categories are physical vapor deposition, or PVD, and chemical vapor deposition, or CVD. These technologies offer different advantages in terms of film composition, conformality, and scalability. Together, they support the diverse material and structural requirements of the semiconductor industry. What is deposition? Deposition is the process of adding ultra-thin layers of materials onto the surface of a semiconductor wafer to construct electronic circuits. These layers can be conductors, insulators, or semiconductors, depending on the design requirements. The building happens layer by layer, starting with a clean silicon wafer as the base. Materials such as metals, insulators, and conductive films are then deposited in a highly controlled sequence. The goal is to achieve nanometer precision, meaning layers that are only a few atoms thick. Key characteristics include nanometer scale control for extreme accuracy, uniform coverage across the entire wafer to ensure consistent performance, and high purity, meaning the process is nearly free from contamination. The deposition process itself is straightforward in concept. First, the wafer is cleaned. Second, the desired material is added. And third, a uniform and functional layer is formed through precise engineering techniques. Why deposition matters? Deposition is the foundation of all modern electronics. Without it, smartphones, computers, and digital devices simply wouldn't exist. It is the core process used to build the circuits and components that power our digital world. Its critical impact spans every major industry. Smartphones rely on deposition for processors, memory, and sensors. Computers need it for CPUs, GPUs, and RAM. Automotive systems depend on it for ECUs and safety technologies, and even medical devices like implants and diagnostics are built using this technique. The benefits of deposition are immense. It enables miniaturization, allowing manufacturers to pack more power into smaller devices. It offers performance control by precisely defining electrical properties at the nanoscale. It ensures reliability, creating stable, long-lasting electronic components. Ultimately, deposition directly affects processing speed, energy efficiency, and the operational lifespan of electronic systems, making it essential to every technology we use. Why deposition matters? Deposition is not just important. It is the economic engine behind the entire semiconductor industry, which surpasses $500 billion globally. This massive market is driven by the continuous advancement and scaling of deposition technologies, which enable the production of increasingly powerful and efficient microchips. Every smartphone tap, every internet search, every digital payment, each relies on semiconductors, and semiconductors rely on thin films deposited with atomic precision. These films form the circuits and structures inside all modern electronics. Without deposition, there would be no transistors, no memory cells, and no interconnects. In short, every digital interaction we have today is built on layers of carefully deposited materials. This foundational role makes deposition not only vital to technological innovation, but also indispensable to global economic growth and digital infrastructure. The impact spans consumer electronics, automotive systems, industrial controls, and cutting-edge medical devices, all powered by thin film technology. Types of deposition. There are two main types of deposition techniques used to build thin films in semiconductor manufacturing: physical vapor deposition, or PVD, and chemical vapor deposition, or CVD. Both serve the same purpose, creating precise functional layers on a wafer, but they achieve it through very different mechanisms. PVD is a physical process in which material is vaporized from a solid source and then transported in a vacuum to the wafer surface. This includes methods like sputtering and evaporation, which are excellent for metals and conductive films. In contrast, CVD is a chemical process where gaseous precursors react on the wafer surface to form a solid film. This method is ideal for producing conformal coatings and complex materials. PVD is typically used when directional deposition is needed, while CVD excels in coating high aspect ratio structures. The choice between PVD and CVD depends on material needs, step coverage, and specific device architecture. Deposition. Deposition processes are essential in semiconductor manufacturing and are divided into two major categories: physical vapor deposition, or PVD, and chemical vapor deposition, or CVD. PVD works through the physical removal of atoms from a solid source. There are no chemical reactions involved. Instead, material is directly transferred to the substrate. Common methods of PVD include sputtering, which uses ion bombardment, and evaporation techniques such as thermal and electron beam heating. On the other hand, CVD relies on chemical reactions. Here, gas phase precursors react on or near the surface to form a solid film. This process can achieve highly uniform and conformal coverage, even over complex structures. Popular CVD methods include plasma-enhanced CVD, or PECVD, and low-pressure CVD, known as LPCVD. Key differences include the nature of the process, physical versus chemical, operating temperature, and coverage. PVD operates at lower temperatures and typically deposits material in a line-of-sight manner. In contrast, CVD generally requires higher temperatures but achieves better conformality. The choice between the two depends on material type, structure complexity, and thermal budget. Deposition. Deposition processes are critical to building the layers that make up modern semiconductor devices. Two fundamental techniques are physical vapor deposition, or PVD, and chemical vapor deposition, or CVD. PVD operates at relatively low temperatures, typically below 450 degrees Celsius, which makes it suitable for depositing metals and simple structures where thermal budgets must be carefully managed. Materials are physically ejected from a source and deposited onto the wafer surface. CVD, by contrast, relies on high-temperature environments, often exceeding 900 degrees Celsius. It enables the formation of solid films through chemical reactions involving gas phase precursors. CVD is ideal for depositing insulators and for achieving coverage over complex three-dimensional shapes due to its conformal nature. In semiconductor fabrication, both PVD and CVD play complementary roles. PVD provides the precision needed for metal layers, while CVD delivers the uniform coverage essential for insulating layers. Together, these methods contribute to building the complete chip, enabling the high-performance, densely packed devices used in modern electronics. Physical vapor deposition. Physical vapor deposition, or PVD, involves moving atoms from a source to the wafer without chemical reactions. It begins by physically removing atoms from a solid target using either thermal energy or ion bombardment. These atoms are transported through a vacuum environment, ensuring minimal contamination and precise control. Finally, they condense and deposit onto the wafer surface, forming a thin film. This entire process occurs under low temperatures, typically below 450 degrees Celsius, which is suitable for substrates sensitive to heat. There are two main PVD methods. First, sputtering uses argon ions to bombard a target, knocking off atoms with high energy, which then travel to the wafer. Second, evaporation uses heat, either thermal or electron beam, to convert the solid source into vapor. The vapor rises and deposits directly on the wafer above. Both techniques rely on a line-of-sight path, limiting their effectiveness on complex or deep structures. PVD is widely used for metals and simple geometries. Physical vapor deposition. Physical vapor deposition, or PVD, is a process that physically moves atoms from a solid source to a wafer. The process begins by removing atoms from a target material, then transporting them through a vacuum, and finally depositing them onto the wafer surface. PVD is widely used in semiconductor manufacturing for its precision and cleanliness. Its primary applications include forming metal layers, contacts, diffusion barriers, and seed layers required for subsequent processing steps. There are two primary PVD methods. The first is sputtering, which uses ion bombardment. In this method, argon gas is ionized to create plasma. These ions are then accelerated toward the target, knocking off atoms that are deposited on the wafer. The second method is evaporation, which uses heat. Thermal evaporation heats the material resistively, while E-beam evaporation uses focused electron beams to heat and vaporize the source. PVD is ideal for simple structures requiring low temperature, line-of-sight deposition, and is critical in building functional interconnects and barrier films. Physical vapor deposition. Physical vapor deposition, or PVD, encompasses two main methods: sputtering and evaporation. Both aim to move atoms physically from a source material to the wafer surface, but each has unique strengths. Sputtering, the most common PVD method, uses ion bombardment to eject atoms from a target material. It provides better step coverage, making it suitable for more complex topographies. However, the deposition rate with sputtering is typically moderate compared to other techniques. Evaporation, by contrast, uses thermal heating to vaporize the source material. It offers high film purity and a fast deposition rate, making it valuable for creating very clean and uniform films. However, its step coverage is not as robust as sputtering, limiting its use in intricate structures. A quick comparison shows sputtering excels in coverage, while evaporation delivers better film quality. Combining both techniques enables the formation of high-performance metal interconnects, critical for enabling reliable chip functionality in semiconductor devices. Each method complements the other in achieving precise and clean metal layers. Chemical vapor deposition. Chemical vapor deposition, or CVD, is a process used to build thin, solid films on a substrate through chemical reactions. It begins when gas phase precursors are introduced into a reaction chamber. Once inside, these gases undergo controlled chemical reactions, often initiated by heat or plasma. The result of these reactions is the formation of a solid material that deposits uniformly across the wafer's surface. CVD typically operates at high temperatures, often above 900 degrees Celsius, which helps drive the reaction and improve film quality. The resulting film is highly conformal, meaning it coats surfaces evenly, even those with complex topographies. CVD is fundamentally a chemical process, distinguishing it from physical deposition methods. It is commonly used in semiconductor manufacturing to create insulators, dielectrics, gate oxides, and passivation layers, making it a foundational technique for building advanced microelectronic devices. Chemical vapor deposition. At the heart of chemical vapor deposition is a fundamental transformation, gas turning into solid. This gas-to-solid transformation is made possible through a series of carefully controlled chemical reactions. In a typical CVD process, gas precursors such as silane, SiH4, and ammonia, NH3, are introduced into the reaction chamber. These gases react when exposed to heat, triggering a chemical reaction that results in the formation of a solid film on the wafer surface. A common example is the formation of silicon nitride, Si3N4. The reaction is SiH4 plus NH3, Si3N4 plus H2. In this case, silane and ammonia serve as precursors. Silicon nitride is the desired solid film, and hydrogen gas is released as a byproduct. This entire process allows for precise film deposition on complex surfaces, making CVD a versatile and essential technique in semiconductor manufacturing. CVD types. Chemical vapor deposition can be adapted through different process conditions to meet various manufacturing needs. 3 common methods include PECVD, LPCVD, and APCVD. PECVD, or plasma-enhanced CVD, uses plasma to activate chemical reactions at lower temperatures, around 400 degrees Celsius, making it ideal for temperature-sensitive substrates. LPCVD, or low-pressure CVD, operates under reduced pressure to produce high-quality, uniform films with excellent step coverage. APCVD, or atmospheric pressure CVD, runs at ambient pressure and offers faster deposition rates, making it suitable for high-throughput applications. Key parameters across all methods include temperature, which ranges from 300 to 1200 degrees Celsius, pressure from millitorr up to atmospheric levels, gas flow rates between 10 and 1000 standard cubic centimeters per minute, SCCM, and, for PECVD, power levels between 100 and 1000 watts. CVD offers significant advantages such as excellent step coverage, uniform film thickness, the ability to coat complex 3D structures, and the production of high-purity films suitable for advanced semiconductor applications. Chemical vapor deposition. Chemical vapor deposition relies on a powerful combination of chemical reactions and high temperatures to achieve precise film deposition. It all begins with chemical reactions, where gas phase precursors undergo transformation into solid films. These reactions are driven and sustained by high temperatures, which enable the complex chemistry needed to form high-quality materials. The elevated temperatures help break molecular bonds in the gases, encouraging them to react with each other and form stable, solid films on the wafer surface. When both elements, chemical reactions and thermal energy, are optimized, the result is perfect conformal coverage. This means the deposited layer can uniformly coat even intricate or high aspect ratio structures. Such consistency is vital in semiconductor applications, particularly for forming insulators and dielectric layers. Together, these components, chemistry and heat, make CVD an essential method for producing reliable and high-performance films in advanced electronic devices. PVD versus CVD. Choosing between physical vapor deposition, PVD, and chemical vapor deposition, CVD, depends on your process goals and material requirements. PVD is a physical process where material is vaporized from a solid source and deposited onto a substrate. It operates at relatively low temperatures, typically under 450 degrees C, and requires high vacuum conditions. PVD offers fast deposition rates, but provides only moderate step coverage, making it less suitable for complex geometries. It uses simpler equipment and delivers good film quality. In contrast, CVD is a chemical process that forms solid films through reactions of gas phase precursors. It typically requires high temperatures above 900 degrees C, but offers excellent step coverage even on 3D structures. CVD's pressure conditions can vary widely depending on the method, and while the deposition rate is moderate, the resulting film quality is often superior. Overall, PVD is favored for speed and simplicity, while CVD excels in conformality and film purity. PVD versus CVD. PVD, or physical vapor deposition, and CVD, or chemical vapor deposition, are two fundamental deposition methods used in semiconductor manufacturing, each with distinct mechanisms and ideal applications. PVD is a physical process, meaning materials are vaporized in a vacuum and deposited as thin films. It's best for depositing metal films such as aluminum, copper, and titanium. Additionally, PVD is commonly used for barrier layers, seed layers, and contact metals due to its speed and effectiveness at relatively low temperatures. CVD, in contrast, is a chemical process that relies on chemical reactions to form solid materials from gaseous precursors. It excels at depositing insulators like silicon oxides, SiO2, and silicon nitrides, Si3N4, and is ideal for gate oxides and passivation layers. Choose PVD when metal layers, low temperature, and speed are priorities. Opt for CVD when conformality and 3D structure coverage are needed, especially for insulating films. PVD versus CVD, advantages and limitations. When choosing between physical vapor deposition, PVD, and chemical vapor deposition, CVD, it's important to weigh both their strengths and limitations. PVD offers several advantages. It is a low-temperature process, making it compatible with temperature-sensitive materials. It produces high-purity films with excellent adhesion and allows for precise control of film thickness. However, PVD also has limitations. It relies on line-of-sight deposition, which results in poor step coverage and makes it unsuitable for coating complex 3D structures. Additionally, it requires high vacuum conditions. On the other hand, CVD excels at step coverage and can conformally coat complex geometries, making it ideal for 3D structures. It also delivers high film quality. But CVD comes with challenges. It generally operates at high temperatures, involves toxic precursors, and requires complex chemical reactions. Additionally, CVD processes tend to have slower deposition rates. Selecting between the two depends on process requirements and material constraints. PVD versus CVD. Key takeaway. The essential distinction between physical vapor deposition, PVD, and chemical vapor deposition, CVD, lies in their application focus and performance characteristics. PVD is a physical process best known for its speed and is commonly used to deposit metal interconnects and contacts. Its main advantage is rapid film formation at lower temperatures, making it ideal for depositing aluminum, copper, titanium, and other metal films required for conductive pathways in semiconductor devices. PVD is efficient and straightforward when dealing with flat surfaces and applications where conformality is not a top priority. CVD, on the other hand, is a chemical process and is especially suited for forming dielectric layers and passivation coatings. It provides excellent conformal coverage, especially on intricate or three-dimensional structures. This makes it ideal for insulators like silicon dioxide and silicon nitride. In summary, remember this: PVD means metals and speed, while CVD stands for insulators and coverage. Each process has its strengths depending on the material and structural requirements. Applications and examples. Deposition technologies like PVD and CVD are essential in everyday electronics and large-scale computing. In processors, PVD is used for forming copper interconnects and aluminum metallization, as well as depositing barrier layers such as titanium and titanium nitride. These layers are crucial for electrical conductivity and diffusion prevention. CVD, by contrast, is applied to gate oxides like silicon dioxide, SiO2, as well as to passivation layers and interlayer dielectrics, which ensure insulation and structural integrity. In smartphones, deposition supports the fabrication of core components like CPUs manufactured with 7 nanometer process nodes, LPDDR5 dynamic random access memory, CMOS camera sensors, and 3D NAND flash memory. Each of these components requires highly controlled thin film layers applied through deposition. Data centers further rely on deposition for high-performance computing. With CPUs exceeding 64 cores, GPU cores surpassing 10,000, and terabyte-scale memory, these systems demand advanced thermal management and packaging, all supported by deposition layers. Finally, the industry scale is immense. Advanced chips require over 1,000 deposition steps, and the equipment market exceeds $50 billion annually, emphasizing the critical role of PVD and CVD in modern technology. Applications and examples. Part 2. Deposition processes like PVD and CVD play a pivotal role across a wide array of advanced technologies. In memory chips, CVD is used for dynamic random access memory capacitor dielectrics and flash memory tunnel oxides, while PVD is used for wordline metallization and contact plugs. MEMS sensors, found in pressure sensors accelerometers, and structural components use CVD for forming dielectric layers and PVD for electrical contacts. In the automotive industry, deposition is integral to engine control units that use microcontrollers with PVD metals. Safety systems rely on MEMS sensors built with CVD films, while power electronics like IGBTs use specialized deposition coatings to enhance performance and durability. For AI and ML processors, advanced architectures such as TPUs, neural accelerators, and neuromorphic chips are built using cutting-edge nodes at 3 nanometers and below, where precise PVD and CVD processes are essential. A typical semiconductor layer stack illustrates this integration. PVD forms metal layers, such as aluminum and copper interconnects, while CVD is used for passivation, gate dielectrics, and interlayer dielectrics. This multilayer integration enables reliable, high-performance semiconductor devices for all industries.